Welcome to AI Paperslop, the YouTube series for AI researchers and ML engineers where we summarize the latest AI and tech papers.
Let's get right into it.
Yeah, so today we are analyzing a brand new paper titled InSight, Self-Guided Skill Acquisition via Steerable VLAs.
Right.
And this is by Maggie Wang, Lars Osterberg, Stephen Tien, Ola Shorinwa, Biajin Wu, and Max Schwager out of Stanford and Princeton.
It's a heavy-hitting team.
For sure. So here is the bottom line for you guys tuning in. Teaching robots new manipulation skills is like completely bottlenecked by the cost of expensive human demonstrations.
Oh, absolutely.
And, if you've ever tried reinforcement learning for real-world robotics, it just gets killed by sample complexity. And, of course, the sim-to-real gap.
Yeah, RL is brutal on hardware.
Right. So the solution this paper proposes is a framework called InSight, which basically makes vision language action models, or VLAs, steerable at the primitive level.
Think like basic atomic motions.
Exactly, like grasp or lift. And it creates this autonomous data flywheel. By using a vision language model specifically, they use Gemini 3 Flash here, to identify missing primitives for novel tasks.
Which is super clever.
It is. It then generates successful practice rollouts completely autonomously and retrains the VLA on that new data.
Learning on its own.
Basically, yeah. And the result is that the robot learns to twist, caps, pour, and sweep with zero target skill human demonstrations.
Wow.
Yeah, it hits up to 96% success on tasks where zero-shot baselines completely fail.
It fundamentally changes the relationship between the language model and the physical hardware. I mean,
Totally.
We are transitioning from these static pre-trained policies to dynamic frameworks that can actively evaluate their own physical limitations,
Right.
They hallucinate a physical solution in a highly constrained way and then compile that new knowledge directly into their neural weights.
Okay, let's unpack this. To really appreciate why the InSight architecture is necessary, we kind of have to look at the severe limitations of current state-of-the-art models.
Yeah, the baseline is important here.
Right, because we have systems like OpenVLA or Pi 0.5, which do a phenomenal job mapping raw visual observations and text prompts straight to robotic motor actions.
Oh, they do, yeah.
But their capabilities are strictly bounded by whatever specific end-to-end tasks were in their training data.
The inherent problem there is that if you train a standard VLA to, say, pick and place a block, it learns exactly that sequence.
Not that one sequence.
Exactly. But if you subsequently ask it to flip that same block, it usually fails entirely.
Because it hasn't seen a flip.
Right. The rotational movement required to flip simply wasn't in the data set.
Yeah.
And the model, it has no mechanism to invent it on the fly.
But the authors realized something fundamental about physical movement, which is that manipulation skills are inherently compositional.
Yes, they're built out of smaller blocks.
Right. Training a standard VLA right now is kind of like teaching someone to bake a cake, but they memorize the entire recipe as one giant, unbreakable, continuous step.
That's a great way to put it.
Yeah, and if you ask them to bake muffins instead, they completely freeze, even though they already know how to crack an egg and stir batter.
Right. They can't isolate the sub-steps.
Exactly. Existing VLAs can't disentangle cracking an egg from the macro concept of making a cake.
And in robotics terms, if you look at sweeping versus scooping, they share the exact same approach and lowering primitives.
Ah, right.
The only difference is that final lateral pushing primitive in sweeping.
So it's just swapping out the last step.
Exactly. And what's fascinating here is when you look at prior work frameworks like CODIS policies or Vox posers, they attempt to solve this by using VLMs merely as test time planners.
Okay, meaning they just plan on the fly.
Right. The language model sits on top of the robot's control system and orchestrates a sequence of existing skills.
But if the skill isn't there,
then the orchestration fails completely. InSight shifts the paradigm. It uses the VLM as an active agent to permanently expand the learned policy.
so it actually updates itself.
Yes, it drives a data generation flywheel that expands the VLA's underlying neural network weights. So the next time it encounters the task, it isn't relying on that top-down orchestration. It has actual muscle memory.
Okay, so if we accept that skills are just Lego blocks, the immediate engineering challenge is extraction. Like, how do you pull those pristine atomic building blocks out of a messy, continuous human teleoperation video?
Because human movement is so fluid.
Exactly. Human demonstrators don't pause between approach and grasp. It's just one fluid motion.
Yeah, so the pipeline solves this, starting with a human teleoperating a known task, like our basic pick and place.
Okay.
Then they use the VLM to decompose the semantic task description into a sequence of expected physical primitives like close gripper or lift upward.
Makes sense.
But the brilliant part is how they actually slice the video. They don't just rely on the VLM looking at video frames to guess when a motion stops and starts.
Because vision models are notoriously bad at that kind of precision.
Highly inconsistent, yeah.
Yeah.
So they ground the segmentation in the pure physical telemetry of the robot.
Which means looking at the data streams coming straight from the robot's joints and end effector.
Exactly. The boundaries between primitives are mathematically segmented based on two primary signals.
Okay, what's the first one?
First, the gripper command velocity. So they look for sharp transitions indicating an open or close action.
Oh, that makes total sense. Like a sudden spike in the gripper motor.
Right. And second, the dominant end effector motions across the translation and rotation axes.
So moving through space.
Yeah, they are constantly monitoring X, Y, and Z translation alongside rotation across those same three axes. When the dominant axis of movement changes sharply, that flags a primitive boundary.
So they pass that segmented telemetry to the VLM alongside the video to label it. Then they fine-tune the Pi 0.5 VLA, which, by the way, uses a Gemma 2B backbone and a Gemma 300M action expert using LoRa, or low-rank adaptation.
Right. Highly efficient fine-tuning.
Yeah. They trained it specifically on these isolated primitive segments. But here's the critical part. They have to add a learned progress channel to the action space.
This is such an elegant detail.
It really is. It's a continuous output ranging from 0 to 1. Because if you break a task into primitive chunks, the neural network needs a temporal termination signal.
It needs to know when to stop.
Exactly.
Yeah.
It needs to know, hey, I have reached 1.0, this primitive is complete, hand control back to the planner.
And that progress channel is what makes the primitives truly steerable, allowing the system to daisy chain them later.
But let me offer some technical pushback on this segmentation process.
Sure.
Breaking unannotated video into exact robotic control steps is notoriously noisy. I mean, you were trying to align a high-frequency robot control loop, maybe running at 500 hertz, with a standard 30 frames per second camera feed.
The mismatched sample rates are a nightmare.
Right. So even with telemetry, how is the VLM getting the exact boundary frames perfectly aligned without a human manually scrubbing the timeline?
It's a great question.
Because if the clipping is sloppy, the VLA is going to ingest garbage training data and learn corrupted skills.
That is a massive pitfall in behavioral cloning. And the authors account for it with a localized path mechanism.
How does that work?
The system refuses to trust just the raw time series telemetry or just the video. It reconciles the two.
Okay.
It finds the end effector delta change point, so the precise millisecond the robot's physical telemetry registers a shift in momentum or direction.
Got it.
Then it cross-checks that exact timestamp against the earliest visually unambiguous video frame using Gemini 3 Flash.
Oh, wow.
Yeah, by forcing this dual modal verification where the physical delta must match the visual state change, the system ensures the training episodes are perfectly clipped before they ever reach the VLA.
So we've solved the disentanglement problem. The robot now understands its basic building blocks, and we have a steerable VLA.
Right.
But that only helps if we want it to do what it already knows. If I hand this robot a completely novel task, say, pour beans into the bowl.
Its existing vocabulary is useless.
Exactly.
Yeah.
It has never seen a pouring demonstration. How does the architecture bridge that gap without a human stepping in to code a pour function?
That introduces the core engine of the paper, the VLM-guided data flywheel.
Let's hear it.
When you give the robot that novel prompt to pour, the VLM planner maps out a sequence using its known vocabulary, but it hits a wall.
It realizes something is missing.
Yeah, it flags what the authors call a primitive gap. It realizes, okay, I can approach the bottle, I can grasp it, I can lift it, but I do not have a skill in my vocabulary to tilt bottle forward.
Okay, so once that gap is flagged, the VLM has to somehow figure out how to execute it physically.
Right.
It proposes gap parameters. But what I love is that it doesn't output raw Python code or complex Bezier curves.
No, that would fail instantly.
Right. It proposes parameters restricted to single-axis motions.
Exactly.
It can choose translation along DX or DZON, or it can choose rotation along roll, pitch, or yaw, accompanied by assigned magnitude.
So for pouring, the VLM might output a pitch rotation along the E-axis of 110 degrees.
And this constraint is the secret sauce. Here's where it gets really interesting for anyone building these systems.
It's so crucial.
It is incredibly elegant. We all know LLMs hallucinate badly when reasoning about 3D space.
Oh, terribly.
Yeah, if you asked a language model to hallucinate a complex, multi-axis sweeping trajectory In 6 degrees of freedom, the degrees of freedom explosion means it would fail almost every time.
It would just crash the arm into the table.
Exactly. But by restricting the exploration space to one single axis and a simple magnitude, you drastically increase the likelihood that the VLM's random physics guess is going to actually work in the real world.
It acts as a highly constrained exploration strategy.
Right.
And during the actual physical rollout, the steerable VLA executes all the known primitives autonomously. It uses its neural weights to move to the bottle, grasp it, and lift it.
Okay.
Then the moment it reaches the primitive gap, the VLA pauses. A deterministic, low-level controller takes over and executes that single-axis motion the VLM proposed, pitching the wrist 110 degrees.
And then comes the magic of the oracle.
The verification step.
Right. After the physical movement stops, a post-planned VLM oracle looks at the before and after scene images. It evaluates if the beans actually went into the bowl.
And if they did.
If the single-axis guess was successful, that specific physical rollout is automatically ingested into the training data set.
It's just added right in.
Yeah, the VLA is retrained via LoRa weight updates, and its vocabulary, its primitive set V, is permanently expanded.
The VLA just taught itself a brand new physical skill, completely unsupervised.
It's wild. But the theory is beautiful, but theories break down in practice.
Always.
Which is why their simulation experiments are so revealing. We need to see how this architecture performs when forced into out-of-distribution territory.
So they put it to the test in the Libero simulation environment.
Right. And they trained the system exclusively on basic pick-and-place demonstrations. Then they prompted it to flip a block.
So to do that, it had to autonomously acquire a rotate block primitive.
Right. The VLM began guessing single-axis rotations.
And how did it do?
Over 479 attempts, the Oracle verified 246 successful rollouts. After retraining the VLA on those 246 successes, it achieved a 75% success rate on the full end-to-end flip task.
Which is huge. And to contextualize how difficult that is, the authors ran a soft actor-critic baseline.
Let's see, yeah.
Right, which is a standard, highly sample-efficient reinforcement learning algorithm designed to maximize entropy and encourage exploration.
A very strong base.
Extremely strong. But given a comparable compute budget, the RL baseline achieved exactly 0% success on the full flip. Zero. It easily learned how to reach and grasp the block, but because continuous control in high-dimensional rotation space is so hard to explore efficiently, it could never figure out the rotation.
It just couldn't stumble onto the right movement.
Exactly. InSight bypassed that exploration bottleneck by using the VLM's semantic knowledge of the world to guess the correct rotation axis immediately.
But the experiment that really highlights the robustness of this system was the drawer closing task.
Oh, this one is fascinating.
Right. Because they trained the base policy only on drawer opening demonstrations. Then they prompted it to close the drawer.
So it needs to acquire the push drawer closed primitive, but it has to start the task from an open drawer state.
Which represents a massive distribution shift. The VLA has an approach primitive in its weights, but all of its training data showed it approaching a closed drawer handle.
It's a completely different visual input.
Yeah, it's like reaching for a door handle, but someone has already swung the door wide open.
Right.
If you just run off pure muscle memory, you're going to reach for where the handle used to be, your hand will close on empty air, and you'll fail the task.
And if you grab empty air in a robotics simulator, the math degrades quickly.
Absolutely.
If it ran that standard approach primitive blindly, the learned progress channel would fail to map to the visual state, and the arm would likely crash into the open drawer structure.
So how does InSight handle it?
To handle this out-of-distribution shift, InSight implements a VLM completion check.
Okay, what does that do?
During the execution of a primitive, it periodically queries the VLM at 2-second intervals. The VLM acts as a real-time semantic override.
Oh, so it's watching as it moves.
Yes. It watches the video feed, and the moment the gripper is adequately positioned in front of the open drawer panel, it interrupts the original approach primitive before the muscle memory can fail.
That is so smart.
Right. It then successfully triggers the new pushing primitive. Because of this real-time visual override acting as a safety net, the robot hit a 100% evaluation success rate on closing the drawer.
100% success from a starting state it had never been trained on. That's incredible.
It really is.
But, as any ML engineer knows, simulation is forgiving.
Very forgiving.
Simulators have perfect physics, zero friction variability, and no sensor noise.
Yeah.
Physical hardware is where elegant theories usually go to die.
Because compounding errors will destroy a perfectly good policy.
Exactly. So does this autonomous flywheel actually hold up on a real robot?
They tested it. They moved the framework onto a 6-degree of freedom U factories arm.
Okay, so a real industrial arm.
Yes. And for context, 6 degrees of freedom means the robot arm can move in X, Y, and Z translation, plus roll, pitch, and yaw rotation, giving it full spatial maneuverability.
Right, the full range of motion.
They gave the system 50 human pick-and-place demos to build its base vocabulary. Then they tasked it with twisting off a bottle cap and pouring beans into a bowl.
Tasks it had never seen.
Never. And the real-world results are stark. It acquired the cap twisting skill with 92% success and the bean pouring skill with 96% success.
Wow. And contrast that with the baselines. The code is Policy's CapEx baseline, which tries to code these movements on the fly, got a dismal 32% on twisting and 16% on pouring.
Ouch!
Yeah, and the standard Pi 0.5 VLA baseline, 0%.
Because it just didn't have the data dicked in.
It completely failed. But the researchers didn't stop at single isolated tasks. They forced the hardware into a long-horizon compositional mastery test.
This is where it gets really hard.
Yeah, they gave it a massive 14 primitive task. The robot had to approach the bottle, grasp the top, twist it open, release, regrasp it from the side, lift it, move to the bowl, and then pour the beans.
That is a lot of steps to string together.
It is. InSight achieved an 80% end-to-end success rate on this 14-step sequence. The CapEx baseline achieved 4%.
So if we connect this to the bigger picture, the math of compounding reliability is what makes that 80% figure so significant.
Walk us through that.
Well, when you are chaining 14 sequential primitives together using a test time planner, your per-step success rate has to be near flawless.
Right.
If your individual steps are even slightly brittle, say, only 80% reliable, then 0.8 to the power of 14 drops your end-to-end success rate to about 4.4%.
Which is exactly the mathematical reality the CapEx baseline slammed into.
Exactly. InSight survives a 14-step sequence because the retraining process bakes the primitive deep into the VLA's neural weights. It isn't guessing physics on the fly, it's executing compiled muscle memory, maintaining near-perfect per-primitive reliability.
And the acquisition process was remarkably fast. I mean, acquiring the twisting skill only took 23 autonomous trials, which was about 40 minutes of wall clock time on the physical robot.
That's practically nothing.
Right. Pouring took 31 trials, about 85 minutes. But crucially, we have to talk about how it handles weight updates.
Because of catastrophic forgetting.
Exactly. After it retrained the neural net via LoRa to learn twisting and pouring, it retained 100% of its base pick-and-play skills. It completely bypassed catastrophic forgetting.
How did they manage that?
The authors achieved this by utilizing a replay buffer during the fine-tuning stage. They didn't just train the LoRa weights on the new pouring data, they mixed the newly acquired rollouts with a sampled batch of the original teleoperation data.
Oh, smart. So it keeps seeing the old tasks.
Yeah, this ensures the gradient updates don't overwrite the foundational movement representations.
They also demonstrated that the framework isn't just overfitting to gripper states by testing it on non-prehensile motions.
Wait, what does that mean in this context?
Things that don't involve closing the gripper at all.
Ah, okay.
Going back to the sweeping example, the Mars rover use case, they had the robot learn to sweep granular debris using only prior demonstrations of scooping.
So no grabbing involved.
None. The VLM successfully identified the lateral push needed for sweeping, and the VLA learned an entirely new mode of physical interaction.
Okay, so we have this incredibly capable autonomous flywheel that avoids catastrophic forgetting and operates in 6 degrees of freedom. But no paper is perfect, and we really need to look closely at the limitations.
For sure.
What are the hard boundaries of the InSight architecture right now?
The most glaring limitation ties directly back to what makes it successful, the single-axis constraint.
Right, it's a double-edged sword.
It is. Because the VLM is mathematically restricted to proposing motions along a single axis of translation or rotation, it severely limits the complexity of the novel primitives it can acquire.
Okay, so what can it do?
Well, if a skill fundamentally requires a simultaneous multi-axis curve, like imagine a complex wiping motion across a curved windshield, or threading a needle where pitch and translation must adjust simultaneously, this specific implementation will just hit a wall.
It wouldn't even be able to guess the right parameters.
No, it's structurally blocked from it.
Yeah. And another big one, the system also still requires manual human resets between rollouts in the real world.
That's a classic robotics headache.
It is. The data generation is autonomous, but the physical environment is not. If the robot knocks the bottle off the table while trying to guess how to pour, a human engineer still has to walk over and span the bottle back up before the next trial can begin.
So it's not fully hands-off yet.
Not quite. Plus, the framework isn't fully utilizing VLM failure analysis yet.
What do you mean?
Right now, if the robot fails, the oracle simply discards the data and tries another random single-axis magnitude.
It doesn't learn from the mistake.
Exactly. It isn't analyzing the failure state and prompting the VLM with, hey, your 110-degree pitch caused the beans to miss the bowl by 2 inches to the left. Adjust your next attempt.
Oh, that would be powerful.
Right. But currently, it just operates on pure trial and error.
However, the path for future work is incredibly clear and actionable. Researchers can expand the VLM proposals to encompass multi-axis waypoints to solve the complex curve issue.
And the reset issue.
More importantly, integrating learned world models could enable true real-to-sim-to-real pipelines.
Oh, doing the trial and error and simulation first.
Yes. If the robot can practice the VLM's proposed gap inside a highly accurate physics-informed simulator first, you remove the human reset bottleneck entirely.
You would just iterate thousands of times virtually.
Exactly. It would iterate in simulation and only execute in the real world once it mathematically knows the primitive works.
So what does this all mean for you, the listener? Why is InSight a paper you really need to pay attention to?
It's a huge shift.
It really signals a structural shift in how the industry is going to deploy foundation models in robotics.
Absolutely.
For the last couple of years, the dominant trend has been using massive LLMs and VLMs for pure test time reasoning, basically, prompting the model to figure out the physics on the fly over and over again.
Which is slow and computationally expensive.
Exactly. InSight proves that a far more efficient and robust paradigm is using these heavy, compute-intensive models to build continuous autonomous data generation flywheels.
You don't want the VLM reasoning through basic physics every single time the robot moves.
No. You want the VLM to generate perfect, verified training data so the VLA can compile that skill directly into its localized muscle memory.
It's the difference between translating a language word by word with a dictionary versus actually becoming fluent.
That's a perfect way to look at it.
It's moving from conscious reasoning to autonomous reflex. And this raises a profound implication, something the authors didn't explicitly test, but which is, the inevitable logical conclusion of this architecture.
Where's this heading?
Well, if vision language models can now act as both the creative planner proposing physical movements and the strict oracle verifying their success, then the human data bottleneck has been fundamentally solved.
Yeah.
The physical environment itself is the only remaining friction point. Imagine what happens when we scale this up from a single benchtop robot arm to a fleet of 10,000 mobile manipulators, all operating in different environments.
Oh, wow.
They said independently identify primitive gaps, physically practice them, verify the successes with their onboard VLMs, and then push those verified lore weight updates to a centralized cloud.
So they all learn together.
Exactly. You would have an entire fleet sharing newly compiled physical reflexes in parallel, completely unsupervised. We are no longer just looking at automated data collection. We are looking at the genesis of true scalable robotic self-play.